Hi, my name is Leong with Matric number 179069. Today I will be presenting on my final year academic project entitled Preparation and Characterization of Nitrogen-functionalized carbon quantum dots. Firstly, I would like to show sincere gratitude to my supervisor, Dr. Suraya Abdul Rashid, for giving me such an opportunity to embark on this project. To begin with, carbon quantum dots have lately received considerable attention by a wide variety of their exceptional properties. Carbon quantum dots are zero-dimensional carbon-based nanostructure materials with a diameter of approximately 10 nanometer. These materials have uniform particle size, excellent biocompatibility, low toxicity, and stable photoluminescence. The previous studies proposed that carbon quantum dots own lower toxicity and wider photoluminescent bandwidth in comparison to semiconductor quantum dots. Functionalization is adding functional groups at the edges of carbon dots that can act as reaction sites and change PL emission by altering their electron density. Nitrogen was chosen as the functionalization atom due to the fact that nitrogen atom possess a comparable atomic size, 5 valence electrons to form strong covalent bonds with carbon, strong electron affinity. Also, it can provide more active sites and enhance interaction between carbon and oxygen. The objective of this study are to calculate conversion yield of carbon quantum dots and nitrogen carbon quantum dots, study methodology by microwave-assisted technology, and investigate the morphology, optical, and chemical properties of nitrogen-functionalized carbon quantum dots. The significance of this study is that a greener and simpler method is used, functionalization with nitrogen, which has been mentioned previously, and contribution to agricultural field and microalgae has been cultivated. In this study, we prepare carbon quantum dots and nitrogen carbon quantum dots with 5 different loadings of nitrogen. Also, characterization techniques including photoluminescence, UV-Vis, FTIR, and FESAM coupled with EDX were performed. Bottom-up and top-down strategies are well categorized for synthesizing carbon dots. Bottom-up method involve growth of appropriate molecular precursors into nano-sized carbon quantum dots by supplying external energy, whereas top-down method involve direct cleavage of bulk carbonaceous materials into nano-sized carbon quantum dots through physical, chemical, and electrochemical process. Top-down method is simpler and easier. So, among the synthesis method, microwave-assisted method was selected because it is rapid, easy operation, and environmentally friendly. Biochar samples used in this study were made from empty fruit bunch (EFB) via a controlled pyrolysis process. Chemical reagents used were isopropyl alcohol (IPA) and urea. All chemicals were used as received without further purification, and distilled water was used throughout the whole study. For the preparation of carbon quantum dots, biochar powder was mixed with organic solvent, which is IPA solution, prepared in the ratio of 1 IPA to 3 distilled water. Microwave assisted of carbon quantum dots was simply attempted by operating the microwave irradiation for 5 minutes and low power settings without any other chemical reagents and treatment. After the reaction, centrifugation was performed. The supernatant solutions containing carbon quantum dots were collected, and the residues on the bottom were rinsed and filtered. The filter paper with residue was dried in oven, and the residue was weighed as unreacted biochar. For the preparation of nitrogen-functionalized carbon quantum dots, different amount of urea was added at the first step of procedure, and the following steps are same as the preparation steps for pure carbon quantum dots. For the characterization techniques, UV lamp is used to observe the fluorescent properties of carbon dots at 365 nanometer. UV-vis spectroscopy is the absorption spectroscopy in UV spectral region. Besides, PL spectroscopy is used to study luminescent properties of carbon dots. FTIR spectroscopy can recognize the functional groups and show the bonding information. Last but not least, FESAM produces magnified image for morphological study, and EDX provide elemental analysis on the scan areas. From the results, nitrogen-functionalized carbon quantum dots show considerably improved conversion yield in comparison to pure carbon quantum dots. The base solution is a clear and colorless liquid. Both of the carbon quantum dots and nitrogen-functionalized carbon quantum dot solutions were colorless and transparent in daylight and emit bright blue fluorescence under irradiation of UV light at 365 nanometer. Compared to carbon quantum dots, nitrogen-functionalized carbon quantum dots show improved brightness. Nitrogen carbon quantum dots with 0.6 gram urea as nitrogen loadings showed strongest blue fluorescence, which implies that functionalization of carbon quantum dots with heteroatoms can regulate their optical behavior. In order to further determine the distinction in optical properties of carbon quantum dots and nitrogen functionalized carbon quantum dots, UV-vis spectra of both carbon dot solution were demonstrated. So the nitrogen functionalized carbon quantum dots show red-shifted peak positions, which may be attributed to the oxygen-containing groups and existence of strong electronegativity of nitrogen atoms. The 228 and 240 nanometer are referred to pi-to-pi star excitation of the bonds of aromatic C-C bond, whereas 300 and 335 nanometer are referred to the N-to-pi star transition of carbon double bond oxygen. Both of the carbon quantum dots and nitrogen functionalized carbon quantum dots exhibited excitation wavelength dependent emissions, which can be arised from different emissive traps caused by wide distribution of differently sized carbon dots and inconsistent surface chemistry on surface of carbon dots. Excitation wavelength with highest emission peak for carbon quantum dots is 300 nanometer, whereas for all of the nitrogen functionalized carbon quantum dots is 250 nanometer. Upon addition of urea, PL intensity decrease, which can be caused by the inclusion of NH2 groups that produce several surface trap levels. Moreover, an interesting PL blue shift was observed, which may be attributed to the strong electron affinity of the functionalized nitrogen atoms. For the FTIR spectroscopy, the figure shows FTIR spectra of carbon quantum dots and nitrogen carbon quantum dots with different nitrogen loadings. The surface functional groups act as passivation layer that facilitates solubility of carbon dots in water and enhance their PL properties. The absorption bands of CN stretching vibrations at 1436 exponential centimeter were observed for nitrogen functionalized carbon quantum dots only, implying formation of CN units in carbon structures of nitrogen functionalized carbon quantum dots. NH bending vibrations at 1560 exponential centimeter also confirm the successful adulteration of nitrogen atoms into nitrogen functionalized carbon quantum dots. For the morphological study, size of carbon dots increase after functionalization because of the presence of functional groups and bonding of nitrogen atoms with carbon atoms at the edges of nitrogen functionalized carbon quantum dots that enlarge the basal plane spacing of carbon dots. For the elemental composition, presence of nitrogen in EDX spectrum of nitrogen functionalized carbon quantum dots confirm its successful formation. A significant percentage of oxygen is originated from the oxygen gas in air and the oxygen-containing solvent used, which is the IPA solution. In summary, a facile, fast and economical microwave-assisted method has been demonstrated to generate carbon quantum dots and nitrogen functionalized carbon quantum dots. So, both of the carbon quantum dots and nitrogen functionalized carbon quantum dots were transparent and colorless under visible light and emitted intense blue fluorescence under the irradiation of UV lamp. Nitrogen functionalized carbon quantum dots with 0.6 gram urea as the loadings of nitrogen emitted brightest blue fluorescence under UV lamp showed strongest PL intensity at optimal excitation wavelength, which is 250 nanometer, and UV vis absorption peaks at 240 and 335 nanometer with highest offset. Functionalization has elevated the conversion yield relative to carbon quantum dots and enhanced the optical performance of carbon quantum dots with the tunable emission of nitrogen functionalized carbon quantum dots. For the recommendation parts, the chemical physical mechanism behind the fluorescence of nitrogen functionalized carbon quantum dots, which have not yet been fully understood, can be further studied. In order to acquire nitrogen functionalized carbon quantum dots with higher conversion yield, different parameters such as reaction time can be adjusted to find the optimum conditions of nitrogen functionalized carbon quantum dots. Moreover, different kinds of heteroatom, for example phosphorus, boron, sulfur, fluorine, and even chlorine, can be studied to find the influence on the formation and luminescence of carbon quantum dots. Last but not least, different characterization techniques such as HRTEM and XPS can be carried out. These are some references that are used in this study. Thank you very much.